All right, we're going to wrap up our work on exponential functions with a couple of videos on exponential growth and decay. Probably one of the most applicable real-world math that you'll work with in Algebra 1. Super, super important to be able to understand. And we'll do an introduction here and then a couple of solved examples. So we are still working under this standard form, a times b to the x, where a is our y-intercept and b is our growth rate, or I'm going to call it our multiplying factor. So are things being multiplied by 2 each time? Are they being multiplied by a half each time for decay, etc.? There's this term I want to talk about called the change factor, which is what you'll see in a real-world scenario that we need to work with to be able to get the multiplying factor. So let's contrast these two equations. And I'm just going to put in some random arbitrary numbers. Okay. So for the first one, this is growth, and the second one is decay, and maybe you can see why. It has to do with the base is larger or less than 1. So if the base is larger than 1, we have growth, and if the base is less than 1, we have decay. If the base is equal to 1, another arbitrary set of numbers, but with a base of equal to 1, no matter what x is, this term will always be 1. So we just have the flat line y equals 36. There'll be no change. Okay. So that's not a common situation, but it's something you need to be aware of. So in this first one, the growth or the multiplying factor is 1.12. Every time x gets bigger by 1, we're multiplying y by 1.12. But the change factor is plus 12% each time, or plus 0.12. So you can think of this as if we had an interest rate of 12%, or if something was gaining in value or appreciating in value each year by 12%, we would get a multiplying factor of 1.12. And you're probably wondering, where does the 1 come from? Where does this 1 come from? Well, that's kind of our starting base level exponential base, I guess. And so if we didn't have that 1, we would just have decay. If it was just 0.12 to the x, we would just be decaying away our initial value of 36. Okay, so that 1 helps us keep our initial amount, and then the 0.12 tells us that we're growing by on top of that by 0.12 or 12%. And then next, this represents exponential decay. So we're starting with 53 grams of some radioactive material, say, and it's decaying away at a rate of minus 8% each time, each year, each hour, we don't know, or minus 0.08. So I call these numbers the change factor. I don't know if every math teacher or every textbook does that, but that's what I call them. And I call, whoops, let me try to delete that. Okay. I call these numbers the bases. I call those the multiplying factors. So they're definitely related, but the multiplying factors has that initial value of 1 that we're either adding or subtracting the change factor to. All right, so let's go ahead and do a couple examples. So money deposited in a savings account might have an annual interest rate of 3.6%. Compounded monthly, so that means every month we get a 1/12 of 3.6% added in to our bank account. So keep in mind that whenever we talk about interest rates, it's almost always an annual interest rate. Okay, so 3.6 averaged overall per year. If I deposit my earnings from my summer job of $2,500, what can I expect the value to be in 6 years? All right, so let's go ahead and start with our core exponential growth equation. Okay, and I think we can see that we're going to have something that looks like this, perhaps. But we're going to have to modify things a little bit. So this, what I'm highlighting right now, what I just talked about, that would be a great equation for 3.6 annual interest compounded annually. So if every year 3.6% was added into our bank account. But that's not the case. So we're going to need to modify that a little bit. So I'm just going to strike through it so you don't think that's correct, but we're going to modify it. So we have y equals 2,500. And I think I said earlier, I hope you recalled, that we're actually getting a 12th of 3.6% added in each month. Okay? And then we can think about how many months have to go by. So this will be 6 times 12 right there, okay, or 72. So we're doing all of this on a month-by-month basis. So we're looking at monthly calculations now. All right, so just to be super clear, this represents our monthly interest rate. We need to add it on to our base value of 1. This represents how many months are going by, 72 months over 6 years. And this represents our initial starting value. So we can just plug this into a calculator and do it. Unless you're super familiar with your calculator, I suggest doing this in a few different steps. And I also suggest when you get that number, try to write out as many decimal places as you can. Okay, it's going to work out a little bit cleaner here. So this turns into 1 plus 0.003 to the 72. So sometimes the division won't be nice and clean like that, and just a tiny difference in rounding can lead to dramatic differences in the final outcome. Okay, so it looks like we can go ahead and do that. And again, unless you're familiar with your calculator, I encourage you to do that first, and then at the end multiply by the 2,500. And do you need to type in the plus? This just turns into 1.003, right? So 1.003 raised to the 72, and then times 2,500. So it looks like our final answer is going to be 3101.75. For a check, I want you to just think about, does that seem reasonable? Yeah, it does. We gained $600. We didn't become millionaires, and we didn't lose money, right? So it seems like it's in the ballpark. Next one is going to go a little bit quicker because we don't have to deal with the compounding, okay? So this one is a decay example. I bought my car in 2003 for $15,500. I estimate that it loses 15% of its value each year. What would be a fair price to sell the car for in 2020? So it looks to me like we have 17 years going by, so X is going to be 17. It looks like our starting value is going to be 15,500. And then we need to think about what our multiplying factor is. So I'm going to write this out as losing 15% per year, so losing 0.15. So this is going to end up being 15,500 times 0.85 to the 17. So every year that goes by, the value of our car gets multiplied by 0.85 compared to by what it was the prior year. Does that make sense? Every year that goes by, the value of our car gets multiplied by 0.85. Okay, so let's go ahead and crank this through our calculator. And it looks like y is equal to, oh my goodness, $978. And 26 cents. So our car gained a lot lost a lot of value. And this is why people say that cars are not a good investment. They're a tool. They're a tool you need to, we often need to have to be able to get around and live our lives. but they're not something that you should think of will gain value. They lose money. All right, that's a good place to stop.